Good day, students. Welcome to the AP Calculus AB exam review. We're going to be doing number 2 of the 2014 free response questions for the AP exam. This question focuses on the area between curves, solids of revolution, and also the volume of solids with known cross-section. Remember that the remaining collection of AP exam worked out solutions can be found on mathgotserved.com under AP Calculus. So before we get started, let's take a look at some formulas that are going to be guiding our problem solving process. So title it formulas. All right, first one has to do with area. So the area formula is basically the integral from a to b of the function on the top, let's call it f, minus the function on the bottom, let's call it g. It could be the function to the right or the function to the left. All right. How do we know the orientation? Well, dx basically indicates a top-down orientation. Function on the top minus the function on the bottom. In this case, the slice, the cross-sectional area of the rectangular region is going to be perpendicular to the x-axis. Or dy is a situation where you're looking at a function to the right minus a function to the left. Okay, in that case, your cross-section, your rectangular region will be pointing to the y-axis. Okay, with this orientation, g is less than f. Okay, either g is to the bottom of f or g is to the left of f. Now, volume is a little bit more intricate. Let's take a look at the formula for volume. So volume is the integral from pi times the integral from a to b of the outer radius, big R square, minus the inner radius r square. Okay, that gives us the area of the washer, and then when we integrate from a to b, we can find the volume. Dx is when your radius is perpendicular to the x-axis or pointing to the x-axis, and then the y is when your radius is perpendicular or points to the y-axis. Now there are two scenarios here depending on the orientation of your axis of rotation. So let's take a look at the two cases. The first one, pi times the integral from a to b. If you're looking at a top-down orientation where top-down or left-right, if the axis of rotation is less than the two functions, we're going to have the function on the top or to the right minus your axis of rotation square. This is big R square. Pi R square will help you find the area of the outer of the bigger disk, minus g minus a square. This is little r square. So pi times that square will give you the area of the inner disk, and then when you subtract these two areas, you get the area of the washer. Okay, so dx, if your radius is perpendicular to the x-axis, or dy, if your radius is perpendicular to the y-axis. All right. So this situation is applicable when a is smaller than both functions. Either it's at the bottom of g and f, or it's to the left of g and f. Okay, and then the other situation we have is pi times the integral from a to b of a minus f. This is big R. The difference here is a is bigger than both of the two functions. Okay, so a minus f square will give you the outer radius, minus a minus g square will give you the inner radius. Dx, if your slice is perpendicular to the x-axis, or your radius is perpendicular to the x-axis, or dy, if your slice is perpendicular to the y-axis. This orientation is applicable when f is less than g and g is less than a. It's like a reversal of the order here. Okay, I always like to put f at the end and then put g in the middle and then a at the other end. So this formula is applicable to revolution, solids generated as a result of revolution. Now, how about the volume of solids with known cross-sectional area? That's very straightforward. that one, the volume is simply going to be the integral from A to B of the cross-sectional area. It could be A of x or A of y, depending. So it's dx if the base is perpendicular to the x-axis, or dy if the base of the area is perpendicular to the y-axis. So this is for cross-sectional area. Let's put that note there, cross-section. The only hard part with this last formula is finding the area of the cross-sectional area, because you have to make use of your geometry formulas to find the area. All right, so let's take a look at number 2, the A part. So it says that let R be the region enclosed by the graph of f of x equals x to the fourth minus 2.3 x to the third plus 4. That's this curve right here. That's f. And the horizontal line y equals 4. As shown in the figure above. Find the volume of the solid generated when R is rotated about the horizontal line y equals -2. All right, so in this problem, let's call the function on the bottom, let's call it f, and then let's call the function on the top, let's call that g. Okay. All right, now it says we're going to want to find the volume when the region is rotated about the line y equals -2. So the question is, where is that line located? The line y equals -2 is going to be somewhere down here. Okay, so what we're going to do is we want to determine what formula that we're going to use to carry out our calculations. Now, what is the direction of our slice, or the direction of the radius? Our radius is going to be going in the direction of the axis of rotation, which is this horizontal line y equals -2. So we are going to have a slice that looks something like this. All right. So what direction is this radius pointing? This radius is pointing to the direction of the x-axis. So everything will be in terms of x. Okay, so let's go ahead and write down our formula. The formula that we went over earlier for the volume of a solid is pi times the integral from A to B. A to B is going to be the points of intersection. So this would be our value of A, the x-coordinate here, and the x-coordinate here. This tutorial is based on the assumption that you already know how to use your calculators to compute the points of intersection, so I skipped that part. So this point has the coordinates 0, 4 if you use your calculator, and then, well, you could figure it out since this y equals 4. That's pretty straightforward. And then this piece right here, the coordinates of this point is 2.3, 4. Okay, you can figure that out by setting these two equal to each other and then solving. Okay, or you can use your calculator also. All right, so what we're focusing on is just strictly the x coordinates. All right, so the formula is the integral from A to B of the big radius square, or the outer radius square, minus the inner radius square, d what? Since we're going in the direction of the x-axis, is going to be dx. Okay, the limits of integration, this will be x equals a, x equals b, a function of x, dx. Okay, now let's go ahead and determine what our big outer radius is and what our inner radius is also. So to do that, I'm going to take this composite radius right here. This radius consists of our outer and inner radii, and I'm going to use that to determine what my big R and little r are. Okay, so I'm just going to draw a straight segment like this, and I'm going to graph 3 points. The function on the top, we call that g. In the formula I showed you earlier, I call that f, but you can call it whatever you want. You never want to get stuck with the symbol. Okay, you have to understand the underlying concept. So let's call that g on top. Let's call this f, and then let's call the axis of rotation a. Okay, so let's see, we want to calculate the how about we calculate the outer radius first? The outer radius, let's just take a look at this orientation first. One thing you want to note is that a is less than f and f is less than g. Our inner function is f and g is the outer function. So this is like the opposite. There's a switch compared to the formula I showed you. Okay. So let's see. For the outer radius, we're going to calculate this length, the length from the top all the way down to the bottom. That will be our outer radius. So how long is that? So the outer radius, this is going to be big R. Big R is going to be the distance from the top to the bottom. So that's going to be G minus A. So that's our outer radius. Okay, now let's look for what our inner radius is. Our inner radius is going to be, let me change my colors here. Let's use blue. Inner radius is basically the length from here to here. So let's make, so let's do this. There's a dotted line. What we're doing is we're calculating how far is it from F to the axis of rotation, okay? So our little inner radius, so little r, in this problem is going to be F minus A. Okay, remember you subtract the bigger one from the smaller one, all right? So this is big R and this is little r. Now that we have our outer radius and inner radius, we're just going to put them into our formula, and that will help us calculate what the volume of the solid is. All right, so let's go ahead and do that. So our volume is going to be pi times limits of integration is x equals 0 all the way to x equals 2.3 times bracket, let's see, what is A? We know that A is -2, right? A is -2, F is that long function right there, x to the 4th minus 2.3, x to the 3rd plus 4, and G is equal to 4. You can use AF and G or FGA, it doesn't really matter, okay? So big R will simply be G of x, G minus A square. Please do not forget the square. Minus little r is going to be F minus A square. Okay, let me use this, F minus A square. And then that's dx. We know what A is. A is 4, right? So we can just use 4 -2, that's what A is. So let's go ahead and rewrite that. So we're going to be inputting in our calculator the integral from 0 to 2.3 of G minus A is minus 2, so it's G plus 2 quantity square minus F minus 2, so that'll be F plus 2 quantity square dx. So this will help us find the volume of the solid when this region R is rotated about x equals -2. Okay, so let me go ahead and show you how to do this with your calculator. All right, I'm going to show you a shortcut that can help you avoid typing the functions over and over again. So what I'm going to do is I'm going to store the functions in their respective locations. Okay, so in this calculator, I am going to be using the TI-89 Titanium. That's the best calculator for the AP exam. I will be storing 4 in G. So let me make a change here. So when you get, let's say you turn your calculator on, turn it back on, you go home, and then you notice what I have for my F1 to F6. I'm going to change that, okay? I'm going to press second function home to have my custom menu. Notice I have F2 there. Now I want to store 4 in my G function. Okay, so I'm going to type in 4, and then above on you have store in function 2, which is G. Enter, tells you done. Now I'm going to store this function in F. So I'm going to have x to the 4th minus 2.3 x to the 3rd plus 4, and I'm going to store that in F2 again, function 1, done. Okay, if you just want to check to make sure everything is correctly stored, let's call the function back up. Let's call on function g of x. Gives me 4, that's good. Let's call on function f of x. Gives me x to the fourth minus 2.3x to the third plus 4. The beauty of this is I don't need to enter these functions over and over again. I can simply use the names of the functions in my computations, all right? So let's go ahead and compute what the volume of the solid is. All right, so let me just go ahead and type this in. So we're going to have the volume is pi. Where's pi? Pi times the integral of, let's enter the, this parenthesis opens the integrand, and I'm going to enter the first square. So we have g of x, f2, 2g of x plus 2, square that, quantity square, minus f of x, f2, the first function, plus 2. Remember, it's x minus a, and a was negative 2, so when you have minus minus, it becomes plus. Close that, square it. Okay, have that down. Now we have to enter our variable of integration, which is x. Our limits goes from 0 to 2.3. And then we close the integrand, the argument for the integral symbol, and then press enter, and then there goes our volume. Okay, so let's go ahead and write that down. Our volume, the volume of the solid is, this is an approximation, is approximately 98, what was it again, 98.868 to 3 decimal places. Okay, so 0.868 square units. All right, so do you know what this solid looks like? Let me go ahead and show you a visualization of what this scenario looks like. All right, so let's go ahead and see how this visualization can help us understand what's going on here. So these are the two functions. Let's go ahead and graph what the rotational volume or solid looks like. So we're rotating, remember, we're rotating about the line y equals -2. All right, so there goes the resultant solid. And next, we're going to alter the axis so you can have a better view as to what's going on with the solid. All right, so let's carry out the same rotation. Right there, so that's the solid we found the volume of. So to compute the volume, if you see our setup right here, we have g of x minus a, that's the bigger radius, and then we have f of x minus a again, that's the smaller radius, and 98.868 to 2 decimal places is basically the volume of the solid that we determined. All right, let's take a look at the B part. So for part B, it says region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of the solid. So in this situation, we first of all, of course, we want to write down our formula because it's going to guide our problem-solving process. Volume of area of known cross-sections, as indicated earlier, is the integral from A to B of the area. Now, is the area going to be in terms of x or y? What axis is it perpendicular to? It's perpendicular to the x-axis, so it's going to be the area in terms of x. Our limits of integration will be x values, d what? dx. All right? So let's go ahead and draw the base of our isosceles right triangle. It's going to look something like that. That's the base. You see that it's perpendicular to the x-axis. Now that's B right there. Next thing we want to do is we want to find out what the area of an isosceles right triangle is. All right. To do that, let's go ahead and make a sketch for ourselves. 1, 2, 3, 4. Okay, let's close the base. and then 1, 2, 3, 4. You don't need to do any fancy drawing here because it's a complicated solid to generate. Okay, so there goes our isosceles right triangle, and this segment right here, let's call that B, and then we also have another base here, B. So what we have is this rectangle rotated and it's sitting right here. Okay, imagine as though you're viewing it from the top. All right, so what is B? Well, before we find B, let's go ahead and determine what the area of this isosceles right triangle is. So this is the right angle right here, 90 degrees. These two legs are congruent by definition of isosceles. Area of a triangle is 1/2 base times height. In this case, the base and the height have the same measure. So the area of this triangle is going to be 1/2 base times base, okay? Because this B is equal to H. So we're going to have 1/2 base square as the area of this isosceles triangle, isosceles right triangle. Okay, so now what is B? To determine B, we just need to figure out the length of this segment right here. Okay, so we know that it's basically looking for this radius right here, in between here. All right, so we know that the length from the top to the bottom, this length right here, is going to be the value of this function. This is g of x, so the length from here to here is basically g, or you can think about it as g minus 0. And then the next length that we need to find, let me put that in blue, is the length from the base of the radius down to there. Okay, we want to figure out what that length is. All right, so let's go ahead and stretch that out. So this length from here to here is how long? Let's put that in blue. The length from there to there is the length from the x-axis to this function. What function is that? That's our f. Okay, let's put that in blue. So that is f. So if the length from the bottom to the top function is g and the bottom to the bottom function is f, then what is the length? What is b right here? What is this length right here? B is simply going to be the difference, right? So B, the base of the isosceles right triangle, is simply going to be the function on the top, g, minus the function on the bottom, f. All right? And we already know what g is, right? G is simply 4, and then it's going to be 4 minus f, okay? So let's go ahead and apply that here. If we apply that here, this is equal to b. We have area is equal to the integral from the lower limit. We already calculated this as being 0, 4 before. We're looking at the x-coordinate since we're perpendicular to the x-axis. From 0 to this point is 2.3, 4. From 0 to 2.3 times the area of the isosceles right triangle, which is 1/2 base times base square, 1/2 b square dx. But we know that b is equal to g minus f, so it's going to be, we'll factor out the 1/2, and then we'll have the integral from 0 to 2.3, and then b is g minus f. We know that g is 4, so we have 4 minus f quantity square dx. All right, and we'll just simply plug this into our calculators to determine what the volume of the resultant solid is going to look like. All right, so let's go ahead and do that. All right, so I'm having some problems with my calculator, my calculator on the computer. So the solution, if you plug in your calculator, should be 3.574. Okay, 3.574 square units. All right, let's take a look at a visualization that will really help us to see what this solid we just found the volume of looks like. So what we're going to do first is basically take this region right here that the rectangle sits on. We're going to rotate it, that the triangle sits on. We're going to rotate it, and then we're going to simulate the movement that the collective triangles go through to generate the solid. And now to create the volume of the solid, that's what it looks like. And then if we stretch it slightly so you can see what it looks like, that's the volume. And then to calculate the volume, notice the setup right here. This is the length of the base of the isosceles right triangle, 1/2 base square, and then you integrate it, find this infinite sum of all the triangles, isosceles right triangles from 0 to 2.3, you get 3.574. Alright, so there you have it. Alright, let's take a look at the last question, the C part. So for question C, we are looking, the question indicates that we are to take a look at the vertical line. So it says the vertical line x equals k divides R into two regions with equal areas. Write but do not solve an equation involving integral expression whose solution gives the value k. Okay, so first thing we want to set up is the expression for the area of region R. We know what the coordinates of the points are, so this point right here is 0, 4, and then this point right here is 2.3, 4. And remember what the formula for area is. This is a function on the top, let's call that f, and then let's call the function on the bottom, let's call that g. It doesn't really matter what you name it, you just have to be consistent with your naming system. Alright, so wait a minute, let's switch this around for a second. Since in the problem we already chose to call the top we chose to call the top g, let's stick with that. So this is g, which is equal to 4, and we call the bottom f, because that's what the question indicated. It called this function f. So the area is going to be the integral from a to b. Since g is greater than f, is going to be the function on the top minus the function on the bottom. And we are going to be slicing this area in such a way that each slice or each rectangle is perpendicular to the x-axis. So this is going to be dx. Okay, so it's going to be a top-down orientation. All right, and then in this case, f is less than g. All right, so that's basically the setup. Now the area of the entire region, so the area of R, is simply going to be the integral from 0 all the way to 2.3 times the function g minus f dx. Now, what is the expression that represents the area of half the region? Remember, this region is being split into two equal areas, right? So if we say we are splitting it down somewhere here, all right, into two equal halves, what will the area of half of the region look like? So let's write that down. Area of, half of the area of R. What will that be? It's simply going to be 1/2 of this expression right here, 1/2 integral from 0 to 2.3 of g, the function on the top, minus the function on the bottom, g minus f dx. Basically half of this area right here. So we're looking for, we want to set up an equation that can help us to find k. What is k? K is that value of x that you have to integrate to, that when you get the value of that area, it's going to be equal to half of the entire area. So k has to be somewhere between these two, between 0 and 2.3. Okay, so how can we represent this area using an integral expression? That is not difficult at all. So that's going to be the area, what we're going to plug into the left side, okay? This area right here is equivalent to the area of 1/2 of the area of region R. So it's going to be a definite integral, of course, from 0 to what? From 0 to k, we don't know what k is, of the function on the top, which is g, minus the function on the bottom, which is f. That is equal to 1/2 of the area of the entire region, which we had set up earlier, 2.3 times g minus f dx. Okay, So this is basically the setup that we can use to solve it. Let me put in all the values here. So integral from 0 to k times g is 4, minus parenthesis, f is x to the 4th, minus 2.3 x to the 3rd, plus 4. Okay, this one, oh, I forgot to put dx here, that's not good. Dx equals 1/2 of the integral from 0 to 2.3 times g, again, minus f, parenthesis x to the 4th, minus 2.3 x to the 3rd plus 4 dx. Alright, so this setup can basically help you calculate what the value of k is to ensure that when you integrate from 0 to k, you have the area that's equal to 1/2 of the area of region R. Alright, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel for updates to other cool clips such as this. And do post a comment to let us know what you think about this presentation. And feel free to share with your friends. And more clips can be found on math.serve.com under AP Calculus. Thanks again for